1-3, friends. Here we go. Can you identify theorems, postulates, and whether they are complete or not? So we're going to start introducing you to the term theorem and postulate. Okay? Geometry is basically an organization of geometric properties and principles. Okay? This was founded by a mathematician named Euclid. And hopefully this year we'll be able to do a little bit of math history with Euclid. Euclid is known as the father of geometry. He lived in Alexandria, in Egypt. He was known for his Elements. That's the book he wrote, a 13-volume book on geometric theory and knowledge. Okay, many famous historians and historical figures studied Euclid, including Abraham Lincoln. He often carried it with him, believing it was vital to becoming a good lawyer. Okay, so the concepts of geometry are based on the laws of deductive reasoning and formulaic proofs. And that's, why Abraham Lincoln said the tools to becoming a good lawyer. So geometry is built upon layers. At the base, you have those three undefined terms we talked about in 1-2, point, line, and plane. Upon those three terms, we build many definitions. Okay? Like I said, begin to get familiar with these definitions and begin to speak the language of geometry. Once we have the definition, we have postulates, and postulates help prove our theorems. Okay? So postulates or axioms are relationships that are assumed to be true without proof. Okay? Our postulates are not exactly something we are going to prove, but we will use postulates to prove theorems. Postulates form the basis of theorems. And theorems are statements that are shown to be true by a proof and logical progression of reasoning. Right? Proofs are verified by definitions, theorems, and postulates. You are going to learn how to set up proofs. You're going to love it. All right. Postulates should be, so remember, postulates are things that do not have a proof. Okay, they're assumed to be true, but they should be consistent, meaning they don't contradict. The definition does not contradict the word and vice versa. They are independent, meaning nothing is being deduced from something else to get to the postulate. And they are complete, which means it forms a sufficient base for full descriptions. Statements can be proved or disproved from postulates. So we're going to look at a couple of examples. Example number 1. We are asked to determine whether the following set of postulates is consistent, which means postulate 1 and postulate 2 do not contradict each other. So we're going to look at this right here. So here are our two postulates, and we're going to look and find out if they are consistent, okay, as long as they do not contradict each other. Postulate 1 says if two lines intersect, then every other line in the plane intersects one of them. Oh, okay, so if I'm thinking about my paper as a plane, and if two lines in a plane intersect like this, then every other line in the plane intersects them. Okay, so that's one postulate. Remember, we're not proving it true or anything, we're just taking it. The second postulate says if two lines intersect, then there is exactly one line parallel to both. All right, so let's kind of break these down. According to postulate 1, every line in the plane must intersect one of the two lines. And that makes sense. If we draw lines like this, or like this, it will work. It will they will intersect one of the two black lines that I drew there. Postulate 2 says, however, that there is a line that is parallel to both. Okay, it says if two lines intersect, then there is exactly one line parallel to both. And it doesn't intersect either. This doesn't work. I can't have, and I cannot draw a line in blue that is parallel to both of the black lines. It doesn't work. Because of this, they are contradictory. And thus inconsistent. Okay? So let's look at a second example. I know this doesn't make a whole lot of, it's not the easiest thing to think of. I'm not going to say it doesn't make a whole lot of sense, but it's not the easiest thing to think of. But we're going to try it again, and we're going to keep trying. Example number 2 says, determine whether the following set of postulates is independent. Okay? So each one has to be able to stand on their own. Postulate number 1, if an animal is named Polly, then it's a parakeet. Oh, okay. Okay. We're going to assume that's true. We're going to assume that's true. If it's Polly, it's a parakeet. Then example number 2, if an animal is a parakeet, then it's a bird. Okay, we're going to assume it's true because it's a postulate. So example number 3, if an animal is Polly, name's Polly, then it is a bird. The third postulate is a logical conclusion that can be derived from the previous 2 postulates. We are using postulate 1 and postulate 2 to make postulate 3. Postulate 3 is not independent. That's like me, if I hadn't even said postulate 1 or postulate 2, that's like me saying, there's an animal there, his name's Polly, so it's a bird. Unless you were given postulate 1 and postulate 2, you would not be able to say that postulate 3 was true. So these are not independent. Okay, postulate 3 was composed based on postulate 1 and postulate 2. Okay. One other term I want to define before we move off of this is the term complete. A system of postulates is complete if it forms a sufficient base for a full description. Okay, so it forms a sufficient base for a full description. Okay. So just kind of stick that in your pocket and understand that it is complete if it forms a sufficient base for a full description. Okay, so we are going to look at incidence postulates. Okay. Excuse me, I had a hiccup. Incidence postulates. Okay. This comes from in, meaning in or on, and cadra, meaning to fall. Therefore, the structure of geometry is built upon these postulates. So these are kind of postulates you need to have in your back pocket. We're not proving any of these true. Okay. We are taking these as truths. Excuse me, I have the hiccups. Give me a moment. So our first incident postulate is the expansion postulate. The expansion postulate says a line contains at least 2 points. A plane contains at least 3 non-collinear points, and space contains at least 4. So I want you to kind of commit this into your head. Okay, line 2, plane 3, and space 4. Those are the number of points you need to define each of these. This falls under your expansion postulate. The line postulate states that any 2 points in space lie in exactly one line. That should be 1. Okay, this means I can take any 2 points and create a line. A line is created from 2 points. The plane postulate says 3 non-collinear points lie in exactly 1 plane. Okay, moving on up. The flat plane postulate. The flat plane postulate says if 2 points lie in a plane, then the line containing those 2 points is in that plane. Okay, if 2 points are in a line, then those 2 points are also in the plane that line lies in. Intersection postulate. I have a typo here, so let's adjust as we go. The line intersection postulate does not say that. I was typing something else. The line intersection postulate says if two lines intersect, it is in 1 point. It's hard to write small with this stylus. Sorry. If 2 lines intersect, it is in 1 point. Lines intersect in a point. The plane intersection postulate says 2 planes intersect, then their intersection is in a line. Okay? If 2 planes intersect, then their intersection is exactly 1 line. Okay, our last 3 incidence theorems are as follows. A line and a point not on that line are contained in one and only one plane. This is hard to think about, and we'll talk about it in class, but here's a line and here's a point. I can create a plane containing both of those. Because by definition, that's 3 points, and it takes 3 points to make 1 plane, right? It takes 2 points to make a line. Add that other point in there, and we can make a plane. The next one is 2 intersecting lines are contained in one and only one plane. 2 intersecting lines are contained in one and only one plane. Again, we're going to look at this in class. It's hard to see in a 2-dimensional drawing. It's a lot easier to see when it's in 3D. Third incidence theorem on this page is 2 parallel lines are contained in one and only one plane. Okay, again, 2 parallel lines, one and only one plane. Okay. So we will look at these tomorrow when we are in class for these. We're going to actually kind of draw these through. Once again, homework is 1 through 25 odd that we will work on in class. Remember on your TRF to please write a nice little summary about what you learned today. Thanks, friends.